This then is the fourth and final video featuring the MadMachine SwiftIO Maker Kit. I suggest you watch the previous videos, otherwise this one's not going to make too much sense. Firstly then we're looking at mission 7, which is controlling the DC motor. It's going to be controlled by the potentiometer module using the Arduino plug-in shield and a PWM motor controller. It says that when we turn the potentiometer, it'll cause the motor to rotate at different speeds. Lastly then we have a challenge to make the motor rotate in the reverse direction. Looking first then at the sketch, we can see there's a brief description, which is what I've just told you, and then we get into the sketch proper, where it initializes the analog pins and the PWM, the pulse width modulated output pin, to control the motor, and there we can see them there. The equivalent of the loop then reads the value from the analog input of the potentiometer and then sets the duty cycle, hence the speed of the motor. Quite straightforward then. I've already uploaded the code to the board. Now when I change the value of the potentiometer, you can hear the motor trying to start up, and there it goes, and we can slow it down and speed it right up again. So very simple pulse width control. As it says though, and indeed this propeller's not blowing, we need to find out how to change the direction of the rotation for the motor. Let's go ahead and work out how to do that. How are we going to go about reversing the motor then? Well, we could just unplug it here, turn it round and plug it back in again, but I don't think that's what's intended. Taking a closer look at the controller board, we can see at the top there the PWM signal, and underneath it another pin labelled DIR. I guess that must be direction. This little device here is a 8833, a Texas Instruments H-bridge motor driver. The DIR pin is connected to the black wire. We follow that back down to the board. The black wire is on the digital pin 11. Using my handy logic probe then, we just test on the ground there. You can see it's low, and the 3.3 volts is obviously high. The direction pin is low, and that's the PWM pin there, which will be pulsing slightly. What we would need to do then to reverse the motor direction is to drive that DIR pin high. Moving over then to the sketch, let's look at the modification that I've done. The first thing here is to create the name DIR for direction and make that equal to digital out of the pin D11 and initialize the port there. Then I'm just going to write that as true or high. Let's get that code loaded onto the board then. We'll press the button there to get it into its upload mode and upload the sketch. Sketch there being downloaded, and we're good to go. The board should now restart, which it has done. Looking now then at the DIR pin with the logic probe, we can see that it's high. And now if I spin up the motor, the direction has indeed been reversed and it's now cooling me down. That's how to reverse the motor. On to the next mission. Our next mission then is to control the servo motor. It's included in the kit. Pay attention when you're connecting the servo to the board. The brown wire here is ground, the red 3.3 volts, and the orange is the signal, or PWM. The idea is that the position of the servo is going to be controlled by the potentiometer. Let's take a look at the sketch, see how that works. Once again then setting the analog input for the potentiometer, a description here of how the servo pulse width modulation works, and defining the PWM output pin for the servo. The loop function, if you will, it reads the value from the analog port, after which it calculates the value to set the pulse duration, and that's translated into the position of the servo arm. Let's see it work now in reality. As I turn the potentiometer, we can see that the servo arm reacts accordingly, and we can position the servo arm anywhere within 180 degrees. Their idea here in the coding challenge then is to see if we can control this using a light dependent resistance, and that will give us a kind of a light meter. So depending on the amount of light falling on the sensor, we can have a different position on the servo. Nothing then to change in the code. It's now reading the resistance value from the light sensor. As we obscure it, the servo moves. Let's see if we can get more light on it as well. So that's full in one direction. So we could put this on maybe a little dial and have some indicator as to the amount of light, or maybe switch something on and off when it gets dark. Mission 9 then is to print Hello World on this LCD display. Hello World, famously one of the first things ever displayed or printed by a computer at Bell Labs back in 1972, I think, when they were testing a C compiler. I guess Hello World is up there with, speaking of Bell Labs, Alexander Graham Bell's first phone call, where he said to his assistant, "Mr. Watson, come here, I want to see you." Rather verbose. And of course not forgetting the first text, "Merry Christmas." There you go, now you can bore your friends this evening. The connection of the LCD module to the board is very simple. What they've actually done is to develop this little I/O board, which is an I²C. So I2C, when you see that, is pronounced I²C. And that uses the SCL and SDA connections and just the usual 3.3 volts and ground. Before this type of connection was developed, you can see all of these pins here, which would have needed to be connected to individual data lines on the board to control it, but now we just need two. Let's take a look at the sketch then. As expected, very simple, just defining the I²C port that we're using and that it's going to be controlling the LCD. Reference number is 1602. Let's get it uploaded to the board then. And there we have our famous message. Our final mission, not only in this video but in our maker kit, is number 10, the Humiture sensor. I've never heard of a Humiture sensor. I can only imagine it's a contraction of humidity and temperature. Anyway, that's what we've got. This is connected to the I²C bus as well. And it's just a tiny little guy there you can just about make out on the circuit board. Looking at the sketch then, there's some math to do to get the numbers into a decimal place. Initializing the I²C port for the LCD and the temperature sensor. The reference for that is the SHT3X. Going ahead then, reading the temperature and printing it on the LCD in degrees C, Celsius. And that's all it does. It doesn't appear to show us the humidity. Never mind. Let's get it uploaded and see what we can see. In this instance, it doesn't seem to have rebooted. Let's just reboot it manually. And there we have the temperature there, 27.8 degrees Celsius. If I then put my thumb over the sensor there, we can see the temperature increasing. As I said then, that's the end of the Maker Kit missions or examples. I think this is a really neat idea. It's obviously early days for these modules. It has great potential. I shall be following it with interest.